Cameras. This session on cameras is also available as a podcast. You should be able to download the video or watch the video on YouTube or Microsoft Streamer. If you are concerned with the usage of your bandwidth, please stop this video. Download the podcast from iTunes, Google Play, or the podcast mobile app or other podcast platforms indicated in the directions below. Moreover, you should be able to download the PowerPoint slides, and in this way you will be able to follow the instructions and you will understand the material. You will have indications such as next or the slide number, which indicated on the lower corner, on the lower right hand side corner, so you should be able to follow the instructions. This is a copyrighted material. If you want
to maximize the use of this session, please connect a headphone and mic if you can. Stay in a quiet place. Adjust the sound of your computer. Close all other programs running on your computer. The instructor will direct you to open any other required program to use. Close chat programs in social media such as Facebook, Twitters, Messengers, WhatsApp, etc. Maximize your screen to see the four corners on this slide on your screen.
The question we start with here is, can we use homographics to create a 360 degrees panorama? If we have an image, and this image will be like the corners you have on the screen right now, either the rectangular blue or red or whatever color. The question is, can I build a 3D image, or can I build more than just a 2D dimension? Usually the answer is yes. If I understand how we capture this image or what is the model of the camera, I will be able to extrapolate the physical environment or the 3D. So if I understand how this camera works, if I understand how I'm capturing this information, and what kind of equation will I use. So in this particular lecture, we will focus more on camera model, and we will describe few different models, and then I will have few examples. How are we solving this problem? So if I want to ask a question is, if I have an object in front of you, and I will have a film in the right hand side. So if you move to the next slide, you will talk about image formation. So an image formation, if I have an object and I have a film, so how can we project this object on a film so we can see it? The basic concept is we will let the camera to get lines, and we expect that these lines from every dot will lead to the film. So as you see here in front of you, that you will have the objects coming with the red lines, and the objects will be coming with the blue line or the gray line if you have this information in gray level. And then you will find there is an aliasing or multi-information, because at the film, for example, you will have two different spots. You will have 4 spots in this particular example. Each spot will receive information from different places from the object. So this will show a blurred image, or this will show a non-coherent, and we call this as a bad camera. So the idea of having an object, and the object will be projected in a film, you need to be able to control that each dot or each point or each location on the object will project only to one location on the film. We can achieve such a thing, and if we move to the next slide, we can achieve such a thing under the title of pinhole camera. So in a pinhole camera, we can reduce the blurring by having a barrier, and the barrier will be a pinhole or a small pinhole. It's basically pinhole, like a small hole in a film, and this hole will focus the information coming from the object to the film. It will reduce the blurring, and this distance of the pen itself, we call it aperture, and in this way an object will send, the top of the tree will send the information only to one spot in the film. And if you keep going in this way, you will notice that every single dot on the objects will go to only one spot on the film. So in this way, we can have a correspondence of one-to-one location. The question will be is how does this transform an image? So having an aperture or having a small pinhole, it's mainly the main model or the most wide used model of any camera right now. So if I can get the equation of how I can create the film here or the image here on the film, you also may notice that this particular image is reversed. So if you see in the object here, the top of the tree is at the top. However, on the film, the red arrow will point to the bottom, which means this is what will continue on the film. It's an inverted image of the actual object. And we quite see that right now if you look at the selfie or some of the phone videos. Sometimes when you take images or videos on the phone, you will notice that the image will horizontally flipped because it basically it will have two sensors inside the camera, and to be able to accumulate the data, they need to work in the same approach by having flipping from left to right, which is very similar from up to down. And in this particular case, they don't have enough time to reverse it. That's why when you record or you do live streaming, sometimes you will see your left hand side on the right hand side of the audience. So the basic principle of the camera is known as early as 470 or 400 before Christ. This basic principles have been known to Moisty, to Aristotle, and Leonardo da Vinci have been using this drawings to give it as an aid, which basically you have here a view outside, and then you have a pinhole in a wall, and the pinhole will go to a specific location. So this pinhole will be focusing the view. As a matter of fact, if you remember some of the location where you can have, like at the birthday of a king or so, you can have lights shining on his statue. This is a very similar principle. However, the focusing of the light, because the sky is wide enough, you may not agree that this is similar, but is similar, which basically we can describe that this particular kind of cameras, without capturing just visualization, it does exist since the Pharaoh's time. So the camera obscura, it's a model which will be used, and as I said, this model have been known from the before Christ times and have been used as a drawing aid for artists like Leonardo da Vinci in the 1400s and 1500s. So this is a concept of the camera itself. So basically you have a box, and the camera will be able to get dots from different location, and then the reflection on the back will give you the actual view of the object. You can make a homemade camera, and this is an example of a homemade camera. You can have here the URL in the next slide, as you see, slide under homemade camera, and you can see the homemade camera, and the question will be in the homemade camera why it's blurry. So if I move to the next slide titled pinhole camera photography, you will see this is an image of 6 months exposure of the northern lights, and this camera has a 6 months exposure. Everything in front of the camera is static, and the northern light accumulations have been seen over the Clifton Suspension Bridge, where it was used only to show the slides. So the following slide called shrinking the aperture, which basically I want to just say, like, if you have a big hole or a wider hole, you will see at a 2 millimeter, for example, the left hand side corner, the top left hand side corner, where you will see the image blurry. If you have 1 millimeter, it will be the right top side image. The lower left, it's a 0.6 millimeter, and the 0.35 millimeter, which is the typical, camera, it will show that the information as clear as it could be. So why, if you shrink the aperture, you will see a very focused, lighter, very detailed image, because you have less light gets through. The diffraction effect from the different lights will not be present, and this is different sizes. So if I want to go to 0.15 millimeter, I will be able to see better. But if I go to a much lower slide, like 0.07 millimeter, I will see the same operation where I will see blurry image again. So in this slide, where you can see 6 different images, you will see the impact of the aperture size or the lens size. So if I will move to the next slide, and I will talk about adding a lens. So what will happen when you add a lens? So when you add a lens, you will see that there is a deflection from the lens, which will focus the same point at 2 different rays coming from this light rays coming from the same point will be focused on the same location. So the lens will be used to focus all the points from the same location into the film area. So the question will be and here's an example of the blue side or the midpoint. So the question will be will I have to place the lens and on a specific distance from the film? The answer is yes. So if you focus the lens at a specific distance from the film, you will reduce what we call it circle of confusion. So when you track the deflection, not the reflection, the deflection of the light ray through the lens, you will find that there is a circle of confusions at certain location, and this circle of confusion means the same point will result in more than one point on the film, and this what will create what we call it blurry image. It's changing the shape of the lens, such as a prism or different shape of lenses, which we'll talk about it later on in the advanced levels. It will control this circle of confusion. Now you understand when you have an SLR camera or a video camera or a camera where you can control the lens location, or you can control the zoom, why you will get from a blurry image into a bigger view. If you move to the next slide, you will see the different location of balls, and each one has a deflection. We also can talk about the Litro light field camera, and this is type of camera where it captures all rays. The lens of this camera, as you see here, you can have the optical axis, which basically is a central line going across of the lens, and then the lens will deflect all the lights ray coming from the subject, and then the aperture behind the camera will create a focal point, and the distance f will be the distance is the function of the shape and the index of the refraction of the lens itself, and the aperture here will restrict the light to achieve a specific point, and then the lens is typically spherical for easy production. And if I want to understand why the lens is spherical, I would love to show you the next slide, which basically talks about the eye. So the human eye is like a camera. We have the iris, we have the pupil, which is the whole aperture, and the iris is colored with the radial muscles, and this iris will control the light. The pupil will show how large is the opening of the hole, and this is very common when you look at the next slide, where before we move away from the eye slide, you will have to understand that the retina, or the back of the eye, is basically where you will have the recorded image. So when you talk about people who have problems with the age that they cannot see far and they cannot see near, it's basically because they cannot control the muscles in the back or in the front to control the stretch of the room or of the cave. If you look at the next slide, we talk about the eyes, and these are the different eyes of different creatures or animals. And some of them is like cats. You see in the night time, you can see the eye is much bigger, wider, and in the light, the eye is more closer because it has to get smaller lights. You obviously, when you wake up in the morning and you have a lights in your front of face, your eye will shrink a little bit or try to close a little bit. You will have in front of you the top rows and the second rows and third rows of each one describe which animal is. Now, does all the eyes are in the nature are pinhole? The answer is yes, and the answer is no, because these are different creatures which they do have pinhole representations. You can move next, and then you can see even the worms. And however, you will see that there are some creatures, they will have more than one lens or more than one eye, but all of them operates in principle with the pinhole operation. So at this particular slide, we covered the pinhole model, and from the pinhole model, we understand that you will have an opening or a pinhole, and the width of the pinhole will control the amount of the light, and the pinhole concept have been used to limit the representation of every point on the target or on the object to the film to be only one point, and then we use a lens, and the lens will control the focusing of the lights themselves. Next, we move to the projection, and the projection is how we can project objects over the back film. So here you can see on the next slide a different projection, which basically will project a sphere into a flat. There is next slide, we talk about the molar layers illusion, and basically if you look at the scenes in front of you, you will have a boy and girl, or a kid and his mom getting tickets, while the dad and the girl going in the theater, they are smaller enough than the parents. So basically you have an illusion, because when you associate points, you may see different objects in different sizes. So however, the size are, if you look at the current slide where you see the parallel lines, you will understand that these parallel lines will give you some size indications. So if I move to the next slide, which is titled Modeling Projections, I want to understand how we will project from the center of 0, 0, 0 of XYZ into the planar space. And if I understand the coordinate systems and I use a pinhole model as an approximation, and I will put the center optics as a center of projections of the region, and I will put the planar as the projection plane in front of the camera, and from this perspective, I will be able to get the camera to look at as a model. So if I understand this projection equations or on this coordinate system, I should be able to reconstruct partially the 3D space. So the projection equation, I want to compute the intersection between the points and the planar space, and I will derive it using the rectangle you can see on the stage here, and then the point XYZ will be minus dx over dz minus dy over dz minus d, and this is the equation, and we get the projection by throwing the last coordinates. So in this case, because the planar itself, its fixed distance on the z order to be d, which is a dimension d, this is constant, And in this case, I will say any point in XYZ in front of the planar will be equivalent to minus dx over z, comma, minus dy over z, which basically is the ratio between between xy and z away from d. So the question is this a linear transformation? The answer is no, because I basically have dividing it by d. So I will use the homogeneous coordinates, which basically I will prolong the vector to add 1. So if I have the tuple xy, it will lead to a vector xy and 1. Or if I am looking at the projection, homogeneous projection of xyz, I will add the tuple 1. And this homogeneous coordinates will transform the equations by 1 into a linear transformation space. So if I want to look at the distance w, which is the distance between the coordinates and the planar, which we call it d in the example before, the homogeneous coordinates will look like xy omega, which will be x over omega y over omega, and it will be also xyz omega if I'm looking for the coordinate x over y over omega, y over omega, and z over omega. So using the homogeneous coordinates is basically a coordination matrix. So I will use the matrix multiplications along the vector, and in this way I will compute to achieve the target of minus dx over z y and minus dy over z. And in this way, this is known as the perspective projection, and this matrix here is the projective matrix. You can also use 4x4 matrix, and if you are using OpenGL, you will be able to get similar information. If you move next, so how does scaling the projection matrix change the transformation? So if I have the transformation here, where I will multiply the transformation instead of minus 1 over d to be minus d, so minus d, and 1. In this way, it will lead to the scale. So basically, the top equation here, I will have both left-hand side and right-hand side divided by d. I will multiply both by d. So in this way, I will be able to get the transformation matrix to be multiplying by d, by minus d, and the right-hand side will be by minus d. The next projection called orthographic projection. So right now we should be at slide called orthographic projection. And the orthographic projection, it's basically telephoto optics, which is in essence, I will have a plane and I'm projecting it on another plane. So in this case, you will have the world as a triangle and the image as a triangle. We also call the orthographic projection as parallel projection, where x, y, and z will lead to only x, y, and it will have what we call it a projection matrix, which you can see it lower there, which basically the projection matrix is 1, 0, 0, 0, 1, 0, 0, 0, and the last column, the fourth column, will be equal to 0, 0, 1. And we multiply it by the x, y, z, and 1. And then this will lead to x, y, and 1, which will lead to the values of the x, y. So you understand, when you have an image, you know the x, y. You know the value x, y. So basically, you try to project what the value z to construct a 3D. Here is an example in the next slide on orthographic projection, where you can see double tables. You can see the a small city in the lower hand side. The next slide will have some examples as well. So I would like to get your attention to the slide where you can see the hallway ending up to 1 point. So this is a perspective projection where you can see the 1 point. So you have the orthographic projections here. in the slide before, and then you will have the perspective projection where you lead to one point. There is a difference, variation of orthographic projections. There is a scale. In the next slide, you call it variance of orthographic projection. You have a scaled orthographic called weak perspective. You have an affine projection called Barras perspective. Affine is one of the common transformation and projection, and I would like to get your attention to it because this has a more valuable, and we will talk about it in the next lectures. So this particular transformation, it gets you from XYZ and to XY. And this is basically the main idea of having the information. So if I want to talk about next slide, dimensionality reduction machine, if I have a word in 3D, I should be able to project it into 2D using this transformation. So we spoke about at least 3 transformations so far. So what do we have? What did we lose when we get from a 3D space? In this particular example, on the left-hand side, you have an individual sitting, and you have a table in front of him, and then you have a wall with a window, and there is a tree behind the window. So the question is, what did we lose? The very first things we lost is basically the angles. So we don't know about the real angles. We also lost the distance. So for example, in the 2D image, you will see the tree behind the screen or behind the window, the tree branches. However, you cannot see how far the tree branches from the window. You will see the table in front of you, and adjacent to it the wall. You will not see the distance. You will also lose the angles. So for example, you can see it's like a prism of the wall to the back wall, but however the corners are basically 90-degree angles in the actual 3D world, because the ceiling is 90 degrees to the wall. However, in the 2D image is not a 90 degree. So some of the projection in the next slide, we talk about projection properties. So there are many to one, which basically any point along the same ray or light ray will map to the same point into the image. So basically you can lose some information. So there are some points will lead to some points. There are some lines which may reserve to be some lines. There are some planes which basically half planes or full planes. And this is an example of parallel lines converting, where some of the lines will vanish. So for example here, if you have parallel lines, it can stay parallel or it can also vanish to a point. So for example here you have the railway, and we know the railway will never meet to a point. So the rails will keep going into same forever. They are parallel forever. However here, because of the projection, they will end up to be in a focal point at the end. So you will feel that the trees are actually closing the railway. So the projection property is another approach to or another area to explore. Then if you have questions here, let me know. So far we talked about and you should have a slide in front of you called question. So far we spoke about the image formation through a pinhole. We talk about the aperture. We talk about the lens itself. We talk about how to remove ambiguity or blurring. We spoke a little bit on how the images are projected into a planar. And if you study geography a little bit, you understand the difference between different projections of the Earth and how to produce maps. Combining all of this information, if you have questions, as I said, you may ask by email or in the forum we have under this video. The next step, we'll talk about camera parameters. How can we model the geometry of a camera? So if I have the world and then I have the camera, so basically the camera will look like a small device which will have a pinhole and it will have a lens. And this camera, as you may see, it will have its own 3D dimension as well. So the idea now of a camera versus the world is basically you have two dimensions, two spaces. Each one has X, Y Z, and you start to look at the camera as XYZ. If you want to talk about global way, and if we do this not a computer vision, but we do it as a video system, you have also a fourth dimension which call it time. However, here we try to focus only on static objects, and then we can talk later on about when they move what will happen. So you can model a camera by mapping the 3D dimension of the camera to the 3D of the image. So in the next slide, we will talk basically on the camera parameters. So to project the points XYZ in a world coordinate of a camera, the first we want to transform XYZ into the camera coordinate. We need to know the camera position, the camera orientation, and we need to know some intrinsic of the camera, which is like the aperture point, the lens itself, and a few other parameters. So if we do know both of these information, we should be able, in essence, to map from a space to another space. The resultant inside the camera is the film or the image itself. So if I can understand the location of the image and how I form the different pixel values, I should be able to extract more about the 3D space. So the camera can be described into several parameters, like the translation T, which is the optical center of the origin. You can have the rotation of the image plane. You can have the focal length. You can have some intrinsic and extrinsic parameters of the camera. In essence, you will have a projection equation, like we spoke about different projections, like perspective and a fine model. We also use some decomposition metrics. So in essence, you will have the 3D world, and then you will have a set. You will have a set of you will have a set of matrices, and these matrices will show how the world itself will be transformed into a 2D image. So the projection metrics will project from a space to another, and here is an example about how the homogeneous coordinate of an image. So once you have an XYZ in the space, and then you have the camera here, and then this plane is basically the image, it will describe how it will move further. You have the extrinsic is basically how they get the camera to a canonical form, the center of projections, and how we transform that by minus C. Then on step we translated. Then how do we represent the translation by a matrix? It's basically a matrix of 3 by 3 with minus C, and the matrix will be basically 4 by 4. And then step number 2 is we do the rotation, and here is the rotation matrix. And then we use in this example the perspective projection, which basically have these two metrics. One converts the 3D ray into 2D pixel, and then you have the aspect ratio, the skew, and the principal point, which could be represented by minus f, minus alpha f, and 1, while s and cx, cy will be the upper triangle matrix. So once you have these equations, you have also what we call it on the next slide called focal length. So can you think of it as a zoom? So basically you have the 25 millimeter to the top left hand side. On the top right hand side, you'll have the 50 millimeter where you can see a little bit of mountains. If you go to the lower right hand side at the 800 millimeter, you have focus where you can actually see the top of the mountain. So this zoom can be different zoom lens based on this zoom lens, and this zoom lens will be also relevant to field of view. So on the focal length, it also can be explained. Then we have what we call it on the next slide called the field of view, and this basically showed how much, when you talk about 18 millimeter till 85 millimeter, how much do you actually see. And you have a URL here, which is how using your own hand you can understand the lens calculator. Then you have the focal point corping, which basically if you have in next slide, you can see a human standing there. You have multi cones. Each one of these cones represent two specific focal points. So the 500 millimeter is a smaller cone, which basically you can see very far but very small field of view. However, if you are on the 180, you can see 180 around you, but you can see very near side. On the next slide, it talk about corbing, where it shows you how the impact of the focal on different lenses. If I want to look at focal point versus viewpoint, which is on the next slide, the telephoto make it easier to see background. Smaller changes in the viewpoint will be bigger, and this will show you how the focal point can impact the positioning of the background. So for example, the top scene, you can see the statue, and then you can see the river. However, if you move a little bit lower, you see the statue and you only can see the back much bigger. So viewpoint is very critical when you talk about long focal points. Here is an example about how the focal point will change up and down. You can see it on video. However, if you don't have the video scene, you will be able to see how you can get the background of the houses. The stone in the middle is still existing, and this particular view will give you an idea how the focal point will work on the telescope. Now, if you go to the next slide, you will see the wide angle, the standard angle, and the telephoto angle. So you can see a face of a lady, and then you can see the same one when you have in a different projection scheme. The next slide, you talked about similar, where you can see the size of the head compared to the back of the body, and all of them are basically different focal point. So on the top left hand side, you can see a relatively bigger, larger face than the back. On the lower hand side, you can see the whole body behind it, because basically you raise the viewpoint. So representing all of this information as a matrix, what you see here is you will have the K intrinsic, projections, rotation, and then translation, and this will get you into how to transfer this into a matrix. Then you can do the matrix multiplication, and from this perspective you should be able to compute the projection using the projection matrix. If you have questions, please write them in the email or write them in the information below. In the next slide, we talk about perspective distortion. Perspective distortion, it's a bigger problem into the architecture view. So if you look at buildings and you take a photo of a building, you will notice that the building has a horizontal line or parallel line. However, the parallel line may not be parallel all the time. So when you talk about the problem of the perspective distortion of a building, you see here on the left hand side, you see the building, and then you see the top floors are much smaller. If you keep the camera parallel to the building, you will see the floors are more parallel. So the idea here is I will have a view camera where the camera itself can change the viewpoint horizontally up and down. So you will be able to look at a building and take an architecture view using the verticals and not having the building as distorted. The same thing for the sphere. So for example, here you have a spherical shape. However, when you look at the spherical shape, it looks like a elliptic or a potato. It's not an actual sphere, and this also a perspective distortion. The exterior column appear to be bigger on the building. So here, for example, I'm in a balcony, and you have these columns in the exterior, and this problem have been pointed out by Da Vinci, that you can see some of them are much bigger. Not only that, you will see the one in the middle looks closer to you than the one on the side. So basically, from the exterior, you will be able to see this column are based on where you can you are actually imaging them. So in the image in the right hand side, it shows the actual 3 column, and if you try to project them in different places, how they will look like. This perspective distortion also look for people. So this, for example, here a group of individuals, and these individuals, when they walk, the one in the front, they will look more closer and much bigger than the one in the back. So looking at distortion, we talk about radial distortion of the image, which caused sometimes by the imperfection of the lens itself. It looks by deviation, are the most noticeable ray which pass through the camera lens itself. Here I will also show on the next slide some of the building view, where you can see how the buildings distortion should look like, which one is bigger, which one is small. I can, on the next slide, we can talk about correcting this radial distortion. So when you do the imaging, in the top image, you can see the building itself. It has distortion in the ceiling, as the ceiling is not, it doesn't look like the real one. In the lower one, you can see the ceiling as pointing as a rectangle, as a triangle. So this distortion, it can be modeled, and here you can see the distortion through the lens, and you can see the column to the right hand side, and under this column you can see that some of the ray will actually be missed, like go to the extreme or get inside, and this is what will cause the distortion. So modeling distortion, which is the title of this slide, project to normal image coordinates is x, y, x, where x over z and y will be y over z. Applies the radial distortion, and this is the equation of the radial distortion, as you can look at in the book, or you can actually use them here. And then you can also apply the final lens, and in this case we can model the lens and we can model the distortion. This projection, we use it instead of the standard projection in a matrix. There is so much types of projection, lots of different variants. There is also the 360 degree field of view as well, and we can take photos of 360 field of view, and you have here in front of you a device which can take these particular images. In this slide we talked also about the tilt shift, which is you can see 2 images, and the one to the lower right hand side is actually of Vegas, where you can see more information but not in the same perspectives. The last slide here, which have rotation sensor on an object, it shows you basically that you can have an object rotation. However, when you take an image, the image can actually be as rectangular or as a cyclic graph. What we discovered in this particular session is different concepts of cameras. You have the pinhole camera, you have the lens camera, you have the planar projection. We explained the multiple projections. We also talk about specific known problems like the architecture, like the correction, the distortion of the lens, how we can move this distortion of the lens. So in this particular section, I appreciate your devotion and following over this presentation. Looking forward to hear from you on the comments below, or send me your questions by email. Looking forward to meet you again in a different module, and enjoy. Have a nice day, and please, if you have any comment on the content or on the quality or in any way, send me an email and I'll be more than happy to reply to you. Have a nice day.